The physical universe is a messy place. It operates on continuous, fluctuating energy, a chaotic spectrum of varying temperatures, pressures, and voltages. But computation cannot tolerate chaos. To process information reliably, computers require absolute, deterministic states, a clean 0 or a clean 1. This diagram shows how engineers force physical reality into mathematical obedience. On the left, a natural analog signal is a smooth, continuous wave. On the right, digital logic ignores smooth transitions, slicing raw voltage into strict binary steps. The mechanism that performs this translation is the logic gate. These microscopic structures act as the exact bridge between raw physical electricity and mathematical reasoning. To understand how they do this, we need to map physical voltages to binary logic, define the foundational rules these gates follow, and verify their operation on a virtual lab bench. Before we can comprehend how a modern processor evaluates a complex algorithm, we have to look at the exact hardware that makes a single automated decision possible. Let's start with the physical bedrock. This scale represents a common operating range for electronic circuits, from 0 to 5 volts. In digital systems, a binary digit, or bit, is simply a conceptual label applied to a specific physical voltage state on this scale. Under standard engineering practices, known as positive logic, we map a lack of voltage to the binary 0. If the circuit reads 0 volts, the system registers a logic low state. Conversely, applying the maximum operational voltage, in this case positive 5 volts, triggers the binary 1. The system registers a logic high. In a physical circuit, you almost never measure exactly 5 or exactly 0 volts. Internal resistance, parasitic effects, and loading cause slight deviations. To prevent false readings, engineers define logic levels as ranges rather than pinpoints. Any signal arriving between, say, 2 and 5 volts is safely interpreted as high. It is also entirely possible to build a system the other way around. In negative logic, 0 volts represents high and 5 volts represents low. The physics remains identical, only the engineering framework applied to it changes. By enforcing these strict tolerance thresholds, unpredictable electrical current is corralled into infallible data. With our binary states defined, we can route those voltages through basic logic gates. These are theoretical circuits designed to evaluate one or more voltage inputs and yield a single, highly predictable output. There are 3 foundational operations. The AND gate requires strict consensus. Its operational rule dictates that the output will only be high if every single input is high. If even one input drops to low, the output goes low. The OR gate is entirely permissive. It yields a high output the moment any one of its inputs registers as high. And the NOT gate performs a simple inversion. It takes a single input and flips the state. A high becomes a low, and a low becomes a high. Combined, AND, OR, and NOT gates can process any mathematical problem in existence. However, physically manufacturing millions of highly specific, distinct gate types across a single silicon die is inefficient and incredibly costly. To solve this manufacturing problem, engineers developed universal gates, specifically the NAND and NOR gates. These combine simple operations into a single package that can be wired to perfectly replicate the function of any other logic gate. We can see the physical reality of a universal gate by looking at this lab sheet for an IC7400 quad NAND chip. The hand-drawn chart maps the 14 separate pins required to integrate this gate into a wider circuit. Before assessing logic, the chip requires operational power. Pin 14 must be wired to the supply voltage, labeled VCC, carrying a positive 5-volt charge. To complete the circuit, pin 7 must tie directly to ground, securing the 0-volt reference point. Looking at the procedural notes for the bench test, we see the actual logic path. Once powered, the test involves feeding 0 or 5 volts into pins 1 and 2, and checking the output on pin 3 by connecting it to an LED indicator. In theoretical math, logic simply exists, but in physical engineering, establishing a stable power supply and solid ground is the non-negotiable prerequisite. Without it, the hardware cannot execute a single Boolean function. With the chip correctly wired, we can test the specific rule of the NAND gate. It produces a low output only when all of its inputs are high. Everything else yields a high. Let's look at the simulation. We apply 0 volts to inputs A and B. Both pins are low. Following the rule, the gate outputs 5 volts, driving the logic state high and illuminating the LED. If we introduce a mixed state, 5 volts to pin A and 0 to pin B, or vice versa, we still lack consensus. The output remains high and the LED stays active. The state only flips under the final condition. By driving 5 volts into both input pins, we trigger the NAND rule. The gate output drops to 0 volts. The logic goes low and the LED shuts off. The NOR gate acts as the opposite universal building block. It yields a low output the moment any single input registers as high. Running these precise bench tests is how engineers calibrate their components. They have to prove that the physical voltages strictly obey the mathematical truth table before layering these logic gates into a billion transistor architecture. Beyond basic and universal gates, we have highly specialized logic, like the exclusive NOR gate. Its specific function is denoted by a dot within a circle in its Boolean expression. The EX-NOR operation is an equality detector. It evaluates two inputs and outputs a high signal only when those inputs match exactly, either both high or both low. To see why an equality detector is necessary, consider an industrial chemical facility. A safety system is tracking two massive liquid tanks, ensuring that both maintain a volume exactly at or above a 25% threshold. We wire the tank sensors into a single EX-NOR gate. If both tanks are safely above the threshold, the gate receives two high inputs and outputs a high, keeping the safety indicator active. If both tanks suddenly drain below 25%, the inputs both drop to low. Because the inputs match, the gate still outputs a high, triggering an emergency response. Instead of wiring multiple and NOT gates to evaluate this condition, the EX-NOR provides a highly efficient single-chip hardware solution for real-world parity detection. When you step back from a single lab bench experiment, you enter the realm of mass manufacturing. These physical gate structures are miniaturized, duplicated, and etched by the millions onto integrated circuits. The hierarchy is absolute. Basic gates provide the core rules. Universal gates deliver manufacturing scale. Exclusive gates manage complex parity checks in a single package. 70 years ago, generating these exact same logical operations required massive arrays of vacuum tubes and relays that consumed entire buildings and required teams of technicians to monitor. Whether built from towering racks of copper or microscopic traces of silicon, the underlying achievement is the same. We have successfully forced the continuous, unpredictable fluctuations of electrical voltage to conform to strict deterministic mathematics. The software you use every day feels fluid, capable of rendering vast digital worlds or routing global data. But beneath that software, a modern processor executing billions of instructions per second is doing exactly what we mapped out on the breadboard. It is simply running billions of physical truth table verifications. The hardware is just frozen logic.
Thanks for watching, and please like, share, and subscribe for such more content and appreciation. Make sure to comment your questions